Good afternoon. So today and Monday, we're seeing a long videotape lecture by Alan Kay. If you don't know the name Alan Kay, you should. He's one of the giants in the history of modern computing, arguably invented every aspect of the modern computing environment. The talk is sort of touches on a lot of different things, so I put up a little roadmap here. Because the first half that we're going to see today is largely about sort of the beginnings, the precursors of the modern user interface design. And then Monday is about human psychology and how relevant it is and how it's relevant and how it contributes to user interface design. Footnote, in the very recent past, we're starting to see new ideas about UI design having to do with the increasing importance of mobile telephones. So there are more people with smartphones than there are with, computers with keyboards. So some things are changing. This talk is from 1980-something, 85 plus or minus 1. So when in the talk, Alan says something about 20 years ago or 25 years ago, add 20 to that. OK, roll it.
This is a talk about the only computer most of us ever see, the one that's acted out on the stage of the screen, called the user interface design. User interface, in many ways, is a second stage of development after the operating system, because the operating system, as we all know, was a layering of software that tried to turn a sometimes poorly designed machine into one that was more fruitful for the software environment. The user interface tries to do the same thing. It tries to design a special kind of machine that's very understandable, very efficient for the person who uses it without removing any of the things that the machine can actually do. This talk is too short to include all of the people that contributed to user interface over the years. I'm just going to pick out a few that particularly struck me along the way and illustrate it by means of examples. So in order to get started, let's go back 25 years to what must seem like the Pleistocene age for most people in universities today, to the dawn of some very important ideas. And first was the very first personal computer, which you see on the slide here. This is a machine called the Link. It was designed at Lincoln Labs in 1962 by Wes Clark, and it's my vote for the first personal computer ever done. You see it has a display and a keyboard, and has some funny little things that look like deck tapes, but were actually originally designed for this machine. And one of the design criteria for this machine was it was supposed to be small enough on the desk so that a person could see over it. So one of the ideas is that this machine should not be intimidating. And about 2,000 of these were built in the 60s, mostly for biomedical technicians who didn't have a mainframe at their disposal and didn't want to hire programmers to use it. They wanted something that they could build, set up experiments themselves, do their own programming. And remarkably, a very large number of the original 2,000 are still in use today, 25 years later. The reason is that, among other things, nervous systems of animals haven't sped up in those years, and so a computer that worked very well back then for doing neurological experiments works very well today. Something else was happening at Lincoln Labs in 1962, and that was the invention of computer graphics. Ivan Sutherland's Sketchpad, probably the most significant single thesis ever done, a remarkable program in many ways even today, as we'll see by looking at this tape. This tape is from the very first movie of Sketchpad, taken in the summer of 1962. So this is 25 years old. Rubber bands you're familiar with, but look at what he's doing. He's pointing at the edges and saying, I want them to be all mutually perpendicular, and Sketchpad just figured out how to do that. Sketchpad is the first system to ever have a window. He's actually drawing on a virtual sheet of paper about 1/3 of a mile on a side. And again, to get something he wants, he simply sketches it in roughly and then gives rules like be parallel and perpendicular, and Sketchpad figures out and solves the problems. Here the rule is collinearity, so that the dashes lie directly over the guidelines below. The Sketchpad was able to solve very complicated problems in real time involving both linear and nonlinear systems of constraints. So it was the first non-procedural programming system and considerably more powerful than the spreadsheets of today. So he's made a hole in the flange, continuously zooms back. Now he wants to make a rivet, and again we see why it's called Sketchpad. He just draws a rough shape, uses the center of the crossbar there as the center of the arc, and then points to the edges and says, I want these to be mutually perpendicular again. Solving that forces the crossbar to change, which forces the arc to change, which gives you a perfectly symmetrical rivet. And he shows that no matter how you distort it, when he turns the problem solver on, it will come up with a symmetrical solution. And he could have made it more complicated. He could have constrained the side lengths to be ratios of each other, or tied to some other drawing in the environment. Now, another important idea seen here for practically the first time is that of master drawings and instances. He was working on a master drawing, and what he has here now is an instance of that. The instance can be rotated and scaled and positioned. So he's going to insert the rivet in the hole. By the way, the Sketchpad was the first system in which it was definitely discovered that the light pen is a very bad input device. So the blood runs out of your hand in about 20 seconds and leaves it numb. And in spite of that, it's been reinvented at least 90 times in the last 25 years. Here's another instance of the rivet, another one. A display is jumping around like that because they didn't even really have computer displays back then. The TX2 is putting up every dot by brute force. He didn't like the cross pieces, so he goes to the master drawing, makes them transparent. Lo and behold, we see dynamically that the rivets, the instance rivets, have felt that change. So Sketchpad is also the first object-oriented software system. And I once asked Ivan Sutherland, how could you possibly have done the first interactive graphics program, the first non-procedural programming language, the first object-oriented software system all in 1 year? He said, well, I didn't know it was hard. There's nothing like this before. And here he's showing that every instance that you make of something, every master can create instances. So he's making a bunch of copies of the hole in the flange. Now, I'd like to tell you where you could go to buy a system as good as Sketchpad, but I don't know where, because there isn't anything like it even on the market today 25 years later. It was a one-of-a-kind thing. It ran on a machine much larger than the studio that I'm recording the talk on. In fact, it was the last computer large enough to have its own roof in the United States. That mammoth machine had all of 460K bytes and executed about 400,000 instructions per second, which meant that this machine, this supercomputer of 25 years ago, was about the size of a 512K Macintosh. So what you saw there on the screen could be done on any of the desktop computers today, but nobody is doing it. Something we should think about just why. Now, moving ahead just a couple of years, we see another pioneer, Douglas Engelbart, the fellow who invented the mouse, the black-on-white display, and the first person to successfully implement hypertext, something that everybody is talking about today. And he did something else that was almost obscene even by today's standards. He actually went and studied his users. So he would poke around in people's offices and see the way people actually worked in offices. And he discovered something funny, that even after 16 years of schooling, the people wouldn't sit hunched over their desks the way they'd been taught. Think of it, a tremendous failure in American education. 16 years of being taught to sit hunched over a desk and people would still scoot around in their office chairs and put their feet up on their desk and so forth. And Engelbart said, well, why the heck should we make people hunch over their desks to use their personal computers? Why not build something into the, in this case, it's a lap board that's built into the arm of the chair, so as the person moves around the room and does all the things they're used to doing with their chair, he is able to also use his computer navigation equipment. Here's an example of Engelbart's system as of about 20 years ago in a live demonstration from San Francisco. He is sitting in San Francisco in an auditorium with about 3,000 people, and his group and the machines and the rest of the paraphernalia are in Menlo Park, about 35 miles away.
The program that I'm going to describe to you is quickly characterizable by saying, if in your office you as an intellectual worker were supplied with a computer display backed up by a computer that was alive for you all day and was instantly responsive, instantly responsive to every action you had, how much value could you derive from that? Well, this basically characterizes what we've been pursuing for many years in what we call the Augmented Human Intellect Research Center at Stanford Research Institute. So look what else we can do in here. I've got this file that's structured. If I want to see what's in there, I can walk down the hierarchy levels and see, or return. But there's another thing I can do. There's a root I said I have here. So here, I'm afraid I'll need a different picture of the view. So here's what I drew with a picture drawing capability here. It's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that, and oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, very interesting. All right. Market. Oh, I've already seen that. Produce and all like that. Gee, that's too much. Anyway, so we have this feature of structuring our material hierarchically, being able to move around it very well. When we get a hierarchy, such as I can show you here now, I can do things if I want to just say, I'd like to interchange produce and canned materials. Bingo. And they're all numbered rightly if I care to look. Interchanging them very quickly. Cans are going to get interchanged with produce. They do it and all gets renumbered. So I have ways of studying over, making different views, moving around, going to specified points, and modifying the structure. At the same time, I've seen that I have a repertoire of different entities, like character, knock off that character, replace the character, make that P. So I have entities of all sorts that I can say I want to do operations on, and this basic structure that I can move over and study and get about very quickly. So that is the essence now. That's the essence of the tool we have. There are a lot of details that I've left out for you. And that's very good feedback. Here are characters that show me the different viewing parameters, view specs. They get large at times at which I can hit single strokes that change those view parameters. And each of those means something to me, and their being large at particular times tells me I can hit very quick abbreviation for changing the view. So I can say, all right, I'd like to go to produce, but I'd like to go to produce, they get big, I'd like to say one branch only, and let me look just that low, and I see it. Oh, I can say, I'd like to see one line only. I can see it. So these ways I move around, the way I get feedback up here, the way I use both hands to coordinate to tell the computer what command and what short literals I want, are all carefully designed to go together to make the repertoire. I'd like to link to Bill and I don't know what his terminal is right now. So I have to ask for somebody to connect me to him audibly. So, Bill, will you come in through this intercom?
Hello, Doug.
Hi. I need to know what terminal you're on, Bill.
13.
Okay. I'd like to have him see my text. And so this special thing, if I label 13, will switch over. So on his display, he sees my text. So I'll execute it. And sure enough, it does. But what's that running around? Well, if he's looking at my text, he'd like to have something to say about it. So we put on a marker, a tracking spot that he controls. So he's sitting in Menlo Park looking at this text, and he can point to it. But we've carefully reserved for me the right to control and operate on this. So my bug is more powerful than yours. But we can have an argument. Yeah. That's what they call a bug fight. So, all right. So, in case you haven't been listening, Bill, we've been going through lots of examples and setting up in collaboration here so that we can go on into information retrieval. And we've set up now audio coupling, and we're both looking at the same display, and that'd be very handy to work. We can talk to each other and point, and maybe later I can hand you the chalk on this blackboard, like saying, here, you control it. But let's stay this mode now and add another feature that hardware-wise is available to the kind of display we have. I'd like to see you while I'm working on it. So before I can do that, I'd have to set up my display in a certain way. Set it up so I see it over like that. That leaves a corner up there, and I say, now, computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it, and I can see your face, and we can talk. So let's do some collaborating.
So Engelbart had a complete vision of what this was going to be like years before all of the rest of us. And the vision included not just some of the ideas about how people were going to react and interact with the machine, but also that since people aren't natural-born hermits, in fact, we're all really communications junkies, Engelbart realized that any kind of a user interface design must include person-to-person collaboration through the medium of the machine. And so as the very first set of ideas that they had, it wasn't just how you organized your information in forms of n-dimensional hypertext, but how you could share it, how you could do something much more than electronic mail, but be able to do direct contact, sharing the information, being able to point, being able to talk to each other, and being able to see each other. We might compare that with the very fragmentary vision of the current-day micro-industry, which is just struggling over decades to try and reach the vision that Engelbart had almost in a complete form as early as 1962. Another thing that's interesting, if we look at the setup here of the mouse in one hand, a regular keyboard in the center, and a 5-finger keyboard on the left hand, we see something that was a very good idea, and we may have noticed something that was also a bad idea. The very good idea, Engelbart realized that you really didn't want to spend most of your time going back and forth between the regular keyboard and the mouse, because you have to find the mouse, you have to find the keyboard, and so forth. Instead, Engelbart wanted to set it up so that you would spend a relatively long period of time in either of those two ways of doing things. Either you'd be typing a paragraph of text, or you'd be doing lots of navigation and fixing single character errors and stuff. And so the 5-finger keyboard working with the 3-button mouse is a way of doing all the things that you could do with the keyboard. So you could stay for a very long time and never touch the regular keyboard. And then the thing that they missed, and they partially missed it because of the inaccuracy of the analog mouse, was the what we call modeless interaction, where you indicate the object first and then give the command. Because the mouse was inaccurate, what they would do in the command, instead of just hitting something like a word or a character or a paragraph and then saying something like move or going to some drag icon, they would have to go and say move word, then wait for a mouse click to indicate which word. And by what you said to move, like move word, move character, move paragraph, the program would know how fine to try and interpret the mouse coordinates it got. Then after it had picked the object, you then had to do a command accept. So in order to move something, you had to do 4 separate actions, which was quite inefficient, even though we'd already set up a more inefficient scheme than we use today for actually using the tools. Kind of an interesting paradox. That's sort of the way it goes. Now, a few years later, 1967 time period, this is the first personal computer that I worked on, called the Flex Machine. Did it with Ed Cheadle. And this is a picture of it on its own display. So by that time, we'd realized that we could build a desktop computer. And of course, this was a desktop computer for only very special kinds of desks, like those made out of steel. So it weighed well over 100 pounds. And it had 2 characteristics that were very noticeable. One of them was it was a tremendous coffee warmer. You know, these little black dual inline packages that hold silicon. The Macintosh has about 50 of them or so that makes up a Macintosh. Back then, you were lucky if you could get 8 or 16 gates in one of these dip packages. And so this machine had about 700 of those and generated an enormous amount of heat and had a fan that was likened to a 747 taking off. The other thing that was very noticeable about the machine is that the user interface tended to repel most of the people that we tried it on. I was a designer of that interface, and I was really crestfallen that people regarded it somewhat the way you would if you lifted the lid on a garbage can and saw something moist and fuzzy down inside. Very puzzled as how could we put all this work into the machine. Had a very powerful interactive object-oriented language that I had derived from Simula. Very high-quality graphics. In fact, it had one of the very first gadgets called the clipping divider, done at the same time as Ivan Sutherland in Harvard, and then later brought out to Utah. Had a very large virtual screen that you could map onto the physical screen. It had multiple windowing, not overlapping windowing because it was a calligraphic display. Lots of good stuff, and yet it didn't fly with the people that we tried it with. And one of the insights as to why this was and what to do about it came from early contact in 1968 with Seymour Papert's logo work at Bridge School in Lexington, Mass. The whole idea of children being able to program on a device that up to now had been in what is called the glass house in industry, it's that big room with air conditioning and raised floor and so forth, the whole idea that this could be extended down into the world of a child just changed my whole conception about what it was. I went from thinking of it, as did Engelbart, as some sort of super vehicle, something akin to a car as compared to IBM's Pennsylvania Railroad. Went from thinking of it as that to something much simpler. I thought of it now as media, because cars we withhold from children until they're 18, though I don't know why. That's when they're most dangerous. But we still nonetheless think of waiting until they're 18. Media, we never think that way. Paper and pencil we want children to start using from the time they can grab a crayon. And so this work of Papert's was critical in our understanding of what was going on. Another thing that was going on at Lincoln Labs was the first iconic programming. It was done at RAND Corporation, the people who did the wonderful interactive programming language JOS. Was done for economists and other non-computer specialists at RAND who had to compute. And one of their complaints about, their only complaint about JOS was, they said, hey, none of us can type. Can't you do something about that? So that led to the invention of the first data tablet. It was called the RAND tablet back then. And this system, from about 1968, called GRAIL, for Graphical Input Language.
This list of processes takes us back to the topmost level, where we may start to edit the flow diagram.
No keyboard whatsoever.
First, we erase a flow arrow, then move the connector out of the way so that we may draw a box in its place.
We recognized he wanted a box and made one.
The printing
now it's
in the box
recognizing
is
his
being
hand printing.
used as commentary only in this case. The box is slightly too large.
Wants to change the
so
size
we
of the
change
window.
its size.
Here's where Macintosh window control came from, literally.
Then draw a flow from the connector to the box. Attach a decision element to the box and draw a flow from it to scan.
Notice that every command is not just iconic, but also analogic.
New area and move
By
the
that
box
I
to a
mean
new position.
that it looks like the thing that you want. So if you want to scrub something out, you scrub it out. If you want to draw a box, you just draw a box. It recognizes you want one, makes one the same size. Chop off a corner.
And label it subscan.
You want characters, you just make characters, and it recognizes those. There are no menus to reach to. You're always looking directly at where you're working. Now notice it missed the N at the end of subscan there. He saw it, he hesitated, but it's the world's first modeless system, so he's able to just go and change it without issuing any more commands. You see every command that's actually being issued, and they're all in the form of direct action.
Complete the diagram from scan to post.
What a remarkable system that was. And when I saw that, I felt, and used it for a half an hour in 1968, I felt like I was sticking my hands right through the display and actually touching the information structures directly. This is the first system I'd ever used, and practically the only one since that I'd call truly intimate. And it was this degree of intimacy that is so important in a user interface. I used to show this movie to my group at Xerox PARC every 3 months or so we wouldn't forget what we're trying to do. Another thing that we saw in 1968 was tiny 1-inch square first flat panel display done at the University of Illinois. And we realized it was only going to be a matter of years until you could put all of the electronics that we had in the flex machine on the back of a flat panel display. You'd have something like this, which I later came to call a Dynabook. Back in 1968, when I made this cardboard model, I just thought of it as the machine of the future and started thinking about what would it be like for millions of people to have one of these machines. And so the metaphor became the pencil. What would it be like to have something like this as extant in the world as pencil and paper? Could people actually use it? And the answer in 1968 and the early 1970s was no. So one of the ways I started thinking about answering the question is, since we'd failed at designing for adults, and I remembered a wonderful phrase of Marshall McLuhan's. He said, I don't know who discovered water, but it wasn't a fish. The idea is if you're immersed in a context, you can't even see it. So we decided to follow Seymour Papert's lead, and instead of trying to design for adults, we would try and see what this Dynabook of the future would be like for children, and then maybe hope that some of it might spill over into the adult world. So children were an absolutely critical factor here. And the first stuff I did in my notebook in 1970 was called Kitty Comp. And here's what it first looked like. It's going to be built out of a Sony Tummy Trinitron. And then Xerox PARC came along with some wonderful, almost open charter funding and a very interesting culture. These are the beanbags that were so famous at PARC. And one of the reasons we used them, we discovered that it was impossible to leap to your feet to denounce somebody once you sat in a beanbag chair, because you tended to sink into it further and further. So it had a way of relaxing people, and it was very good for design. And then we started experimenting. So we built this machine, which was a very, very high resolution way of displaying video images. And the first fruits of that was this font editor, the first font editor done by Ben Laws. And all of a sudden, you could get images like this. That it was quite possible to mimic the high-quality printing images on a bitmap display. We got very interested in that. Trying some of these ideas out on children, we discovered they didn't always like their, you might zoom in on that, they didn't always like to have their rough drafts look like they've been printed by the New York Times. So some of the children said, well, what we really would like to have for rough drafts is our own handwriting. So they used this font editor and put in their own handwriting. And that was a way of instantly telling when you looked at a document just how finished it was intended to be. And the bitmap display also allowed us to do sketching and drawing as well as crisp computer graphics. And again, one of the things that had not been possible before is doing real design on a computer. Before, people always designed on the back of an envelope and then brought the back of the envelope to the computer as a way to render it. But here, what we'd hope for is that people would actually stay with the computer for the better part of the day. And we put a lot of effort into making this display be something that you could look at for 6 or 7 hours without eye strain. Next envisionment of this was a little system we called Minicom, and this was the summer of 1971. And we went to a considerable direction in thinking about making this. And then we also did some dynamic animation, as we'll see in a minute. Space War had a very important part in the design of things because it was a conceptually simple precursor of all of the video games we know today. It should be something that a child could write for himself. And we started working on Smalltalk, an object-oriented language based on Simula, but also with a lot of look back to what Sketchpad. Then all of this led to the Alto computer, built mostly by Chuck Thacker at Xerox PARC, the first workstation, and led to all of the subsequent workstations, and it also led directly to the Lisa and the Macintosh at Apple. We used an improved version of Engelbart's mouse, and in its early stages we call it the Interim Dynabook. We brought lots of children into PARC to work on these machines, and then we took the machines down into the Palo Alto schools, working with several hundred children in all. Here we are at Jordan Junior High School around 1976. Now let's take a look at animated versions of some of the things that ran on this machine and some of the things that the children did. So here's the famous Dynabook model, and back then we wanted it to be like the Hewlett-Packard calculator, except to be a real live computer. This was the inspiration for all that we were thinking about, is what it was going to be like. Here's Ben Law's font editor being used to make an A in Lydian cursive. Most of these are taken from home movies we shot with a 16mm Bolex. Here's the painting program. This is something I designed in the summer of 1972, and Steve Purcell implemented it. Here you see some hand character recognition. It recognized the letter C as a command for drawing circles. That was put in by John Schock. We were experimenting with this at the time. Here's an L for drawing lines. One of the nice things about hand character recognition is that you don't have to move very far to hit something. Here's a D for drawing, which fires up the painting program, and I think you can see it has most of the features of the well-known Mac Paint on the Macintosh. The idea of actually being able to fashion your brushes right in the combination of canvas and palette itself was something that Purcell thought up, I think. The idea of having charcoal and airbrush effects was something that was also added at the very beginning of this program, putting in specular reflections. Here's an example of making a little brush, a bunch of different dots, pick it up, and you get some charcoal effects. Here's some experiments with the very first experiments with windows, dragging them around by one corner, opening their size at the other corner, just like on the Mac today. Making another one by going up to the upper right-hand corner, typing something in it, clipping the stuff that's inside. I think this was the very first actual test, although we, of course, we knew Windows were going to work because there had been examples of Windows before. But this is the very first test of them on a bitmapped display and some experiments with the user interface, what they might be like to just manipulate them. Here is one of the very first group of kids. I can tell that because there aren't even display covers on the display. We had to put in old cardboard boxes to keep the kids from getting electrocuted. This is a group of, I think, 6th graders, 5th or 6th graders, and this is Adele Goldberg, who later went on to head the group after I left Park, and she was responsible for many of the ideas in teaching the children. We first did logo-like things in Smalltalk, such as this program. And we also experimented with animated windows. Here's the very first test of an animated window, which we later abandoned because the machine wasn't quite fast enough. But I still think it's a nicer way of doing it, where instead of getting just an open frame that moves, you actually animate all the text itself and have it occlude the window. So this is the Alto screen in early 1973, not long after the Alto had first started to work. The Alto is actually a very powerful computer. If you could get to its microcode directly, we could. And the Alto is able to animate about 120 square inches of graphics in multiple planes. So you could do very complex 2.5D animation effects. And this is something done by Purcell, I think, around the end of 1973. And that was really the machine we thought we had. It was a machine that you could animate everything on it. Tying all that stuff together with Smalltalk, we got a number of interesting things with the kids. Here's one of the second level classes. This was a 13-year-old teaching 12-year-olds. And Marion had done one of the very first tools in Smalltalk the year before when she had learned it. And she was a very outgoing, ebullient young lady, and she wanted to teach a class. And so we brought in, we had 5 machines at the time, so we had 5 children, and we videotaped all of the 100 hours of it. And here's an example. This is from 1975 of a program that looks very much like MacDraw. It's an object-oriented graphics illustrator. You can select by means of selection handles. You can change colors. You can change the size. So the menu is being used on the lower right-hand there, and the feedback is coming in the window in the center. And the only thing that's really interesting about this program is, besides that it was done in 1975, which is before you could buy it in a store, is it was actually conceived, designed, and implemented by a 12-year-old girl after only a few months of programming in Smalltalk. It took her about 2 weeks to do this, and the size of the program in Smalltalk 72 was about a page long. So part of our aim here was not just to get people to be able to access things by means of the windows, but also to be able to do the equivalent of writing short essays and having them have great effect. And one of the things that is disturbingly true about most novices on computers is that about 2 pages of program is the maximum they can handle. They like to be able to spread it out, use their visual field as an extension of their short-term memory. Here's another example. A 15-year-old boy, again after a few months of programming in Smalltalk 72, he was interested in ham radio, but really had gotten bored with the tedium of drawing radio diagrams, so he decided to make himself a ham radio illustrator, and has some quite sophisticated features. You see here a pop-up menu with often used things like open and close dots. And he has a more extensive menu of iconic shapes for the circuits down below. So he can pick up a battery symbol and rotate it and put it in. This was also done in 1975. And it's one of my favorite programs done by a child, because less than 10 years before this, a PhD had been awarded for a system that wasn't as good. This program is about 80 lines of code long in Smalltalk 72. Now next, we have a program done by adults, but for the most part, who had never programmed before. They were professional animators that came to Park in the summer of '74. And the thing that animators would like to do is to see whether their animations are going to work before they have to go to film. So that summer, they devised a variety of systems. And this is what every animator would like to do, is draw the picture, reach over into the movie window, grab the thing you've just drawn, show it what to do, have it play back. Now, of course, it's not squishing when it hits, so it doesn't look quite real. So he goes to the steps there in the iconic menu. And when it gets down to the bottom here, what he's going to do is replace that with a fresh drawing that's going to come from another transparent cell that he overlays in the drawing windows on the right-hand side. So the drawing windows can have several transparent cells overlaid each other. He uses the old one for registration purposes. So he's now drawing on another cell, and that drawing will be inserted into the animation as the animation goes. And now the animator can see how much detail he has to put into that squash drawing before we see it as actually squashing. And he obviously has to at least put in the specular reflection on the ball. There he goes. And now we see it as a deformation, even though it's a one-frame change. That program was about 5 pages long, which is longer than children can actually do. But here's a 12-year-old girl that was very interested in horses. And so she spent some time getting the correct gait and animating a horse across the screen. But then she wanted a feature that the adult animators hadn't put in, and that was to be able to combine 2 animations into a single one. So she has the horse animation going over there, and here she has a jockey animation. And she wants to be able to pick it up, and in the act of actually combining, she wants them now to fuse into one drawing. This is a feature that she was able to put in herself, because even though she wasn't capable of writing a 5-page program like the adults, she was quite capable of reading it and making a change in it. And here's the finished animation. Now, what we've just seen are some things that are familiar to us now in this day of the microcomputer. We've also seen some things that people aren't yet doing. People don't usually sit down and do for themselves a complete tool like an Illustrator. They go to the store and spend several hundreds of dollars, and yet here we see 12-year-old children coming up with the idea and being able to implement it, and not only being able to implement it, but being able to implement it in a very compact form. Now, why is that, and why is this such an important part of computer literacy? Well, I think literacy has 3 important parts to it. There's an access part, and in the print medium we call that reading. Somebody else makes up the material, and we have the skills to penetrate that material and understand it. Access literacy. The second one is creative literacy. We don't think a person is literate if all they can do is read. We think they should be able to write. And the English language is powerful enough in its metaphor that we can do very strong expressions of our own intent in just a page or 2. We can start a revolution with 2 pages of well-couched prose. Programming languages just haven't been strong enough and easy enough to understand. But if we're ever to have computer literacy, it is going to have those two things as first-order attributes. And then the third thing in computer literacy is that for anything that we can be literate in, there is a literature. So when we read Shakespeare, we have to read Shakespeare with a completely different approach to the genre of the Elizabethan age than we do from reading Mickey Spillane. So throughout the many centuries in which the English language has existed, there are different genera that we have to be able to adapt to. And that's the third form of literacy, is genre literacy.
Yeah, it's great. Next time, we'll see the part about psychology and how it affects design. By the way, the Engelbart demo that you saw in Sketchpad had like 50th anniversary parties a year ago or so. So that's how old that stuff is. And when Alan says, I'd like to tell you where to buy something this good, you still can't. So we'll talk a little bit about why that is, too. See you later, Monday.